In previous lecture, we have discussed the conditions for phase equilibrium. Now, we are going to discuss particularly the first order phase transition, in which we will derive a particular equation which is called Clausius-Clapeyron equation. And this equation results from the first order phase transition, and this is the cause it is said that the first order phase transition is simply the Clausius-Clapeyron scheme of phase transition. And in introductory class, I have just defined the first order phase transition. So I am going to remind you that in the first order phase transition, there is a discontinuous change of internal energy and a specific volume of our system, and this transition takes place at the cost of heat energy. That is, heat energy is either evolved or absorbed during this transition. So you may say, again I am just repeating this fact, that the first order phase transition is accompanied by a discontinuous change of internal energy and a specific volume. You know, a specific volume means volume per unit mass, and simultaneously in this transition, you know, heat is either evolved or absorbed. It means this transition takes place at the cost of heat energy. So in case of first order phase transition, definitely heat energy is evolved. Now, to discuss this first order phase transition, let us take an example, a common example of the transition of a liquid into its vapor state, or a vapor is condensed into its liquid state. So let us consider a closed vessel, and inside this vessel there is a liquid, and that liquid is heated, and after heating it transformed into vapor state. So say this is liquid state, or you may say this is phase 1 and this is its vapor phase, and this is phase 2. And both of these phases are in equilibrium. As just in previous lecture we have discussed the phase equilibrium, the same condition is here. And the system is isolated, so the total mass of the system, total energy, internal energy of the system, and total volume of the system will remain constant. But as mass of each phase will change, volume of each phase will change, and you may say all the extensive properties of each phase will change. So we discuss our concept not in terms of these properties, but the specific value of these thermodynamic properties, which are mass dependent, then our calculation will be concrete and we can easily discuss it. So let us consider the first phase is in fact liquid, and this is phase 1, and the second phase is vapor. Or you may we may take just reverse, that vapor is condensing in liquid state or liquid is vaporizing. You may take anything, and suppose we consider liquid as a first phase and vapor as second phase. Now, if we consider that V is a specific volume, we write the symbol in a small letter for a specific values. S, that is a small s, will represent a specific entropy of the system. A small u will represent a specific internal energy, A small g will represent a specific Gibbs potential. Let us suppose. Now we consider, let M1 and M2 be the masses of the two phases, and G1 and G2 are a specific Gibbs potential for the two phases at any moment. Then in this condition, for the whole system, if capital G is the Gibbs potential of the whole system, then what will be it? Since G1 is the specific Gibbs potential of first phase and M1 is mass of the first phase, then what will be the total Gibbs potential of first phase? That will be simply M1 G1, and that of the second phase will be M2 G2. Since this potential is also an additive property of the system, so when we will add the Gibbs potential of the two phases, understand it like this. If we consider capital G1 is the Gibbs potential of first phase, then this will be M1 G1, because G1 represents the Gibbs potential of unit mass and M1 is its mass, so M1 G1 will be the total Gibbs potential of first phase. And similarly, the Gibbs potential of second phase will be M2 G2, and when we will add these two, we will get the Gibbs potential of our closed system. And so if we take a change in G, a small change in G, what will be this? Since G1, G2 are a specific value of Gibbs potential, so they do not change. Only during the phase transition, masses of the two phases get changed. So this will be G1 dm1 plus G2 dm2. Say this is equation 1. Now, as I have told you that the first order phase transition takes place at a constant pressure and temperature. So this is just an isothermal isobaric process. So as the process is isothermal isobaric, and you know in isothermal isobaric process Gibbs potential of the system remains constant, and so dg will be 0. And if dg is 0, see the above equation, we will have G1 dm1 plus G2 dm2, this will be equal to 0. And say this is equation 2. Again, as the system is isolated, so you have already seen in the previous lecture that in this condition, total mass of this isolated system will be constant. And if this is constant, then what will be dm1 plus dm2? This is 0, and this implies dm2 is equal to minus dm1. So if we substitute minus dm1 instead of dm2 in equation 2, then what will be our result? Our result will be G1 minus G2 dm1, and this is equal to 0. As dm1 is not 0, so G1 minus G2 is 0, and this implies G1 is equal to G2. So the specific Gibbs potential of the two phases will be equal, and this G1 G2 is equal at what pressure? When pressure is P and you may say temperature is T. In this P and T condition, the specific Gibbs potential of two phases are same. Now, if we really change the temperature of the system, then more liquid will convert into vapor, and vapor pressure will change in such a way that this condition G1 and G2 remain satisfied at all temperatures and pressures. So if we consider that temperature is slightly increased, say temperature becomes T plus dt from T, then for equilibrium we will again have the similar condition as defined in 3 for G. So if in a real process if T becomes T plus dt, then corresponding change in G1 and G2 are dG1 and dG2. So we may write, so we may write G1 plus DG1 equal to G2 plus DG2, and this will happen when P is now P plus dP and T is T plus dt. Slightly this, or you may say only this T is equal to T plus dt. But as we have seen in the above equation, that is, see this equation, G1 is equal to G2, so we may say from this result that dG1 is equal to dG2. Say this is equation 3a. Since G1 is equal to G2, so we may write this. Now, as we know, Gibbs potential G, that is a specific Gibbs potential, is a function of temperature T and pressure P. So we may find dG from here, and therefore what will be dG? This dG will be equal to, we know, del G by del T at constant P dt, and plus del G by del P at constant T dP. Say it is equation 4. Now, by definition of Gibbs potential, we know from definition of Gibbs potential, we know that this G will be equal to U plus PV minus TS. Here, small u, small p, small v and small s all represents the specific values of the quantities, and G is also a specific Gibbs potential. And from here, what we will see? We will see that this dG is equal to du plus P dV plus V dP minus T ds minus S dt. And from first law of thermodynamics, this du plus P dV is what? This is del Q, and second law says this is T ds. So you may write this is T ds plus V dP minus T ds minus S dt. Now this T ds will cancel out, and the result left is dG equal to V dP minus S dt. So we will have dG equal to what? This is V dP minus S dt. Say it is equation 5. Now compare the equation for dG in 4. See here, this equation defines dG, and equation 5 also defines dG. So comparing these two equations, we can find V and S. So comparing 4 and 5. What will be V? V is equal to del G by del P at constant T, and S equal to minus del G by del T at constant P. So we have defined V and S in terms of the specific Gibbs potential G. Now, from equilibrium condition defined in equation 3a, dg1 equal to dg2. So you may write, so from equilibrium condition equilibrium condition 3a. What this equation states? This states dg1 is equal to dg2. So, making use of equation 5, you can say this dg1 will be what? This will be v1 dp minus s1 dt. And what will be this dg2? This, see equation 5, this will be v2 dp minus s2 dt. And so rearrange the term. After rearrangement, we will get dp by dt equal to s2 minus s1 over v2 minus v1. And now let us use a simple algebra. We simply multiply in numerator and denominator by the factor t of this equation. T s2 minus s1 over t v2 minus v1. But we know this t s2 minus s1 is what? This is heat absorbed by the system when its phase is changed from phase 1 to phase 2, and that is the liquid state is just converted into vapor state, and this is called latent heat of vaporization, or you may say a specific latent heat, and this is denoted by the symbol L, or you call it a specific latent heat. So this will be equal to L over T V2 minus V1. So finally I write this equation here. This is dp dt equal to L over T V2 minus V1. Actually, this very equation is known as Clausius-Clapeyron equation. This is Clausius-Clapeyron equation. And you know here L is a specific latent heat. So you see that how I have find the Clausius-Clapeyron equation dealing with the idea of first order phase transition. And applications of this Clausius-Clapeyron equation have already been described in the previous lectures in the application of Maxwell's fourth thermodynamical relation. So that's all for today. We will discuss second order phase transition in the next lecture.